Greetings to everyone. We are from Group 1. Today, my members and I are going to explain about the electromagnetic field theory through this video. Here are the following contents that we are going to talk about today in this video. We'll start with Faraday's law of introduction, followed by 3 ways of electromotive force generation, and last but not least is a brief explanation of practical example. Now, I'll start off the presentation by introducing Faraday's law. On 29 August 1831, Michael Faraday is credited for the discovery of the electromagnetic induction. Based on his experiment, there are 3 observations obtained by Faraday. The first one, when the battery is turned on, there is a deflection in the galvanometer. The galvanometer is actually an instrument for measuring a small electrical current or a function of the current by deflection of the moving coil. The deflection is a mechanical rotation derived from forces resulting from the current. Secondly, when the battery is turned off, there is also a deflection in the galvanometer, but in an opposite direction from the first one. Thirdly, later demonstration has also shown that a moving loop would also cause a deflection in the galvanometer. This is because, according to Faraday's experiment, a static magnetic field produces no current flow. However, a time-varying field produces an induced voltage, also known as an electromotive force (EMF), which causes a flow of current in a closed circuit. So if we base on the second picture, we can see that when there is no relative motion between the magnet and the coil, the magnetic flux within the coil remains constant, so the galvanometer shows no deflection. However, when the magnet is moved towards the coil or vice versa, like diagram A and C, there is actually magnetic flux changes and EMF is induced in the coil. In conclusion, from Faraday's experiment, the electromotive force can be expressed as the following equation, where the negative sign shows the induced voltage acts in such a way as to oppose the flux producing it. This behavior is described by the Lenz's law. This one. Moving on, lambda is actually the flux linkage, where n is the number of turns in the circuit, and the magnetic flux is the flux through each turn. Based on this equation, we can conclude that the magnitude of the induced EMF is actually directly proportional to the rate of the change of the magnetic flux, while its direction is depends on the magnitude of magnetic flux. Therefore, Faraday discovered that the induced voltage in any closed circuit is equal to the time rate of the magnetic flux linkage by the circuit. So if we set the number of turns of circuit n equals to 1, then we'll get this equation over here. And knowing that in lecture 17, we have already learned that in magnetostatic field, the magnetic flux is actually equal to the integral of the magnetic flux density. Hence, when we substitute it inside this Faraday's law equation, then we'll get this equation over here. Thus, the variation of flux with time, as in the above equation, may be caused in 3 ways. Firstly, transformer EMF. Secondly, motional EMF. And thirdly, transformer EMF plus motional EMF, which will then be further explained by my members. Thank you.
Hello to everyone, my name is Kareem Mahmoud Sayed, and today I am talking about a condition in Faraday's law which states what would happen in a stationary loop with a time-varying field, or we can refer it to as a transformer EMF. So let's talk about theory for a little bit. It's well known that a current carrying conductor produces a magnetic field. Also, the inverse of this statement is true. A magnetic field can produce a current in a closed loop circuit, but the magnetic flux linkage by the circuit must be also changing with time. So what does that mean? What about our equations and theory? So let's take a deeper look. So using Faraday's and Maxwell equation, we get the following. So in order to get the V of EMF, we are going to integrate partial B over partial T, with B referring to the field and T referring it's the whole concept, time varying B field with respect to ds. As we can have a look here, we can increase the B of t, and this is our field, and at the same time the induced can, like, there is just to make it a little bit clearer, this arrow, like if you're talking in dimensions, is pointing down, not to the sideways, it's actually pointing down. So moving forward, so by applying Stokes' theorem to the middle term, which is grade E equal partial B over partial, the integral of partial P over partial T with respect to ds, but the middle term that we are referring to is this part over here. But there is a catch. For the two integrals to be equal, their integrands must be equal, which is grade of E equal to the negative rate of change of the magnetic field B. These two terms must be equal to each other. This is one of the Maxwell equations for the time-varying field. It shows that the time-varying E field is not conservative, which means that grade E cannot equal 0. This does not imply that the principle of energy is broken or violated, but the work done in the taking charge is in a closed path in a time-varying electric field. I hope this clear this part, and thank you all for listening.
Hi everyone, my name is Chai Bin Cheng, and now I'm going to discuss or do a presentation about motional EMF. So, what is motional EMF? Basically, motional EMF can be defined as a motional EMF is an electromotive force EMF induced by the motion relative to a magnetic field B. This means that when there is relative movement between the conductor or circuit to the magnetic field that passing through it, then the motional EMF will be induced to the conductor. This kind of EMF is also called as flux cutting EMF. And motional EMF mostly can be found in electrical machines such as motor, alternator, and so on. There are two hints that can be used to determine whether the circuit or the conductor is induced motional EMF or not. The first hint is the magnetic field is constant. And the second hint is the circuit or the conductor is moving. There are two equations that can be used or which are related to motional EMF. The formulation of first equation can be start with the Faraday's law. Faraday's law states that VEMF, the induced EMF, equals to dV over dt. Therefore, our V for motional EMF is equals to the integration of magnetic field B dot product with the total surface area, which is varying with time. This is because motional EMF is the circuit is varying with time, but the magnetic field is constant, as mentioned before. By substituting it into this equation, we can get a mathematical equation, which is our first equation of motion EMF equals to d differentiation of integration magnetic field dot product with the total surface area of the circuit or the conductor over dt. So this is our first equation that is related to motional EMF. For the formulation of second-main equation, we have to know that the origin is actually based on the previous lecture, the concept of work done on charge, which is the potential difference is equals to the enclosed integration of electric field dot product with the total length of circuit or the enclosed loop. For electrostatic field, the potential difference will equals to 0. But for our case here, it is not equals to 0. Therefore, it will become this mathematical equation, which is our motional EMF equals to enclosed loop integration of enclosed loop EM dot with the DL dot product with the DL. The EM here is known as motional electric field, which is a special field, and we have to find this special field. We start with the above situation or example. An enclosed loop of the circuit, which the conductor rod is moving to the right and experiencing the magnetic field passing through it. In EMT, we always take sample and do analysis. The sample taken from our conductor here is dq equals to rho v dv. E because when we enlarge or magnify this rod, what we can get is the volume charge. Therefore, from the concept of magnetic force, which is df equals to sample current cross product with the magnetic field density. Our sample current here is our volume current, which is vector j dv then cross product with the vector v. As we know, the convention current density, the one of the model current equation is vector v equals to rho v dot with the vector u. The convention current density is then substitute into this equation. Then we can get df equals to rho v dv vector u cross product with vector v. Hence, our magnetic force is equals to dq vector u cross product with vector v. The concept of electric force and magnetic force is actually quite similar. So we can compare two equations of forces. By comparing these two, we can see that the E is actually equals to the vector u cross product with the vector v. Therefore, we can get EM equals to vector u cross product with the vector v, which is our special field, motional EMF fields. After we get this EM, we substitute into this equation here. Hence, we will get our second equation that is related to our motional EMF, which is equals to enclosed loop of integration vector u cross product with vector v, and then dot product with total length of the enclosed loop or the conductor. This is our second main equation, which is related to motional EMF. There are a few things that we have to know. We can determine the direction of motional EMF by using Fleming right-hand rule. Therefore, the direction of induced EMF is in this direction. And the second thing is, due to the Lenz's law, there will be an opposite force in this direction, with causing the conductor rod moving in right side with constant velocity. That is all from me, and my next member will continue the presentation. Thank you.
Hi guys, I'm Lim Yong Shen from Group 1. I'll expand on the third case, which is the moving loops in time-varying fields, or we can call it as hybrid EMF. So what is hybrid EMF? Hybrid EMF is a moving conducting loops, or maybe a conductor, in a time-varying magnetic field. So in this case, both transformer EMF and motional EMF are present at the same time. So for the transformer EMF, we'll have the circuit remain as stationary and we'll have the magnetic fields changing with time. But for the motional EMF, we will have the constant magnetic fields, but the circuit is moving with a velocity. So in the hybrid conditions, we'll have the changing magnetic fields and also the moving conducting loop as mentioned before. So why hybrid EMF is most commonly being implemented in the real life? This is because it has the most optimal design to generate induced EMF. So this is the hint for us to identify the hybrid EMF cases. So the magnetic field is changing with time, so we'll have BT, and also we'll have the circuit or the conductors is moving with a velocity, so we'll have V naught. We'll have two equations. The first one is the Faraday's law. Faraday's law states that the VEMF in any closed circuit is equal to the rate of change of the magnetic flux linkage by the circuit. So we have the equation here. So the lambda is actually the flux linkage and also the times. So this is the same equation with this. And also we have the second equation. VEMF is equal to the transformer EMF sum with the motional EMF. So this is the equation for the equation 2. V EMF is equal to the formula for the transformer EMF sum with the motion EMF. For these two equations, I think my teammates already mentioned before. So I'll explain on this. There's another kind of equations evolved from this one. So we can get one of the Maxwell equation. This delta close E is equal to the rate of change of the magnetic flux from the transformer EMF by using Stokes theorem. And also we can using Stokes theorem to get this equation from the motion and EMF from this equation to become this equation by using Stokes theorem. So the del close EM is equal to the del close U close B. So to finalize these two equations, we have the del close E is equal to the negative rate of change of the magnetic flux, magnetic field, plus with the del close U close B. So that's it for me. Thank you.
Hello, my name is Fadila Rahmat Hairani and want to explain about real-life example in EMF. And our example will be on Faraday's law, transformer EMF, and motional EMF. First is Faraday's law. In 1831, Faraday made a groundbreaking discovery. He wrapped a tube in copper wire and insulated it with cloth. Next, he hooked the copper wire up to a galvanometer, which could measure electric current. When he passed a magnet backwards and forwards through the middle of the tube, the needle on the galvanometer moved. He had created the first ever of electricity. Most of the generators that exist today basically use the principle of Faraday's law, although different energy sources such as water, steam, wine, oil, coal, or a nuclear reaction will produce motion. If we look at every power plant using the same concept, moving the turbine, the only difference that the energy that drives the turbine can be water, wine, coal, or something else. And second is example on transformer EMF. A transformer is an electrical apparatus designed to convert alternating current from one voltage to another. It can be designed to step up or step down voltage and works on the magnetic induction principle. Transformer is useful so that less energy is wasted during the transmission process. Usually in everyday life, we use a step-up transformer when we just produce electricity from a generator. Then the energy moves to another place and use step-down transformer that meets specifications so the devices in that area can use it safely. And the last is about motional EMF. Motional EMF is useful for producing motion energy from electricity. If previously the generator produced electricity from energy source, and this motion is opposite, many uses in daily life such as toys or electric cars, which have been developed recently. And an electric car stores electric, and it's different with a common car that store oil in a tank. If a common car moves because moving pistons, an electric car moves because motional EMF.